So here we start talking about solutions. And the definition is that first and foremost, it is a homogeneous mixture. It can consist of two or more substances, and solutions form when the attraction between the molecules of solute and solvent is high enough to be energetically beneficial. There are two or more components, solvent and asolute or solutes. So solvent is present usually in much larger amount compared to solutes. I will give you an example when it is not exactly true. The solute is present in a smaller amount. So for example, when you make the solution of salt in water, the amount of salt that you add is much smaller than the amount of water you add the salt to. Solutes themselves can initially have any physical state. They can be liquids, they can be gases, or solids. The important thing about the distribution of solutes within the solution is that this distribution is even. In other words, if you sample any part of the solution, the ratio between the particles of a solute and the particles of a solvent, this ratio is going to be the same. We call this ratio a concentration. Now, when a solute and a solvent are mixed, the solution remains in the physical state of a solvent. The important thing about solutions is that the solvent and the solute cannot be separated by filtration. However, they can be separated by the evaporation. Solutes are not visible, but in some cases they do give the solution a color. In this example for here, on the left, you can see the copper 2 sulfate. At the bottom of the graduated cylinder, which also contains water. On the right, you can see the same cylinder, but in this case, copper sulfate is dissolved in water, and that even distribution is quite clear, and indeed copper 2 sulfate will give the water the blue color. So solutes and solvents can be of very different types. Of course, we're going to focus on the water solutions. So for instance, air is an example of gas in gas solution. Carbonated water is an example of gas in water. Vinegar, or any, for that matter, any like alcoholic drink, would be a solution of liquid in liquid. And seawater or the tincture, iodine tincture, would be like betadine, would be the solution of solid in liquid. So far, we good? Or there can be a solution of solid in solid, which would be alloys, such as brass or steel. We're going to focus on water, being the solvent. Most important biological solvent. Remember, water is polar. And water molecules can also form hydrogen bonds. We already discussed the importance of hydrogen bonds in biological systems. This is why water is a great solvent for many different biological molecules. So, fundamentally, the formation of a solution can happen when, let's say you have, let's say this is the molecule of solute, okay, two molecules of solute, interacting with each other, and you have adjacent to them molecules of solvent interacting with each other. And if the interaction between the solvent and a solute gives you energy benefit if the forces that attract solute and solvent particles are greater than individual forces that, keep them separate, you're going to have a solution. Okay? So, why we care about this so much? Because if you look at this example, there are three different solutions. I'm going to focus your attention on these two. In these cases, these liquids do not mix. Can you see that? And they probably don't mix because one of them is polar and another is non-polar. And that brings us to the rule of the like dissolving like. So, polar substances will dissolve in the polar solvents. Non-polar substances will dissolve in non-polar solvents. If you combine a polar substance and a non-polar solvent and vice versa, you're not going to get yourself a solution. And I'm going to give you some examples. If you take, so water is a polar solvent. Does everybody agree with that? So salt, sodium chloride, is an ionic compound. So it is like superpolar. Okay? Will salt dissolve in water? Yes. If you will mix salt and oil is nonpolar. Will salt dissolve in oil? You think so? Try it at home. It will not. Salt will not. Did I say oil? Yeah. No, it will not dissolve in oil. Yeah. It will be like mixed with it, but it will not be true solution. Okay? Now imagine you working on some outdoors paint project. If you spill the paint, do you use water to remove it? No. You use like in the name, but like a paint thinner, right? Paint thinner is non-polar. And so are paints. Does that make sense? So these are examples when polar dissolves polar and non-polar dissolves non-polar. So an interesting thing happens when ionic compounds get dissolved in water. So sodium chloride is a simple ionic compound, but that consists of two ions, positive sodium and negative chloride, right? But interestingly enough, positive sodium can form electrostatic interactions with partially negative, remember, partially negative oxygen, so positive sodium, partially negative oxygen, they attract each other. Negative chloride gets attracted to partially positive hydrogen atoms in water. So the ions become hydrated, or more general term is solvated, if we use some other solution. Okay? Now, you may notice that ionic compounds in solutes, ions separate. Make sense? So we can say that ionic compounds dissociate in aqueous solutions. Aqueous solutions, which is really important. Now, an example of, methanol or ethanol are both polar compounds, not ionic but polar, and they dissolve in water because water is a polar solvent. So, for example, here you can see on the right, you can see the molecules of methanol forming hydrogen bonds with water molecules. Sounds reasonable? Yeah? Now let me ask you something else. Can you, do you think, actually dissolve salt in methanol? Let's start.
No.
No? Well, let's start with this. Salt. Why can you dissolve salt in water? Because salt is what? Ionic. And water is what kind of solvent? Polar or non-polar? Polar. Methanol, is it polar? Yes. Can you dissolve salt in methanol? You can. Nobody does it because there's no specific reason for it. You're probably not going to be able to dissolve as much salt as you can in water, but you can dissolve some. Okay? So let's talk about what is solute and what is solvent in each of these solutions. So let's start with this. A, what is solvent and what is solute?
Sugar is solute and water is solvent.
Excellent. Solute. Solvent. Ethyl alcohol and methyl alcohol, look at the numbers.
60 is solvent. 30
Yes.
is solute.
Yes, this is solvent and this is solute because they're simply less. What about the next one?
Water is solvent and sodium chloride.
Yes, solute. And here, air, solvent, nitrogen is solvent, and oxygen is solute. So let me present you a curious case. Imagine that you are trying to make a syrup, right? But you want really, really thick syrup, okay? So you need to dissolve a lot of sugar in water. You follow. So you start heating water up. And you keep adding sugar. Let's say you have 1 liter of water. It's 1 kilogram, right? I'm going to skip all the graph, but I can tell you that if you get water almost to the boiling point, you can dissolve up to 2 kilograms of sugar in 1 kilogram of water. So technically, there is more sugar, right? But since it's still liquid, and that's important, the solution is still liquid. Sugar is not liquid, water is. So we consider, in this case, the physical state of solvent trumps the amount. Are we clear? Okay. So, when lithium chloride is added to water, what is attracted to what? So, lithium is attracted to oxygen or hydrogen? Oxygen. Oxygen atom because it carries partially negative charge. And when you look at chloride, obviously, hydrogen atom. Okay? So, what will dissolve in water? This is salt, sodium sulfate. Will it dissolve in water? Gasoline. Iodine. This is the molecule. Why? Really? Two iodine atoms form a bond. Will any of them be able to pull electrons towards itself? Two identical iodine. Remember the analogy with brothers? This is two identical twins. They have to share their Xbox in the same way. Is that clear? Yeah? Yes? Okay. Perfect. Hydrochloric acid. Well, hydrogen chloride, it's not the acid yet. I can tell you the electronegativity. Chloride, 3.5. Hydrogen, 2.1.
No.
Do you remember the definition of covalent polar bond? So, nonpolar, the difference in electronegativity, I'm going to call it delta E, is less than 0.44 or equal. Polar, 0.4, 1.8. Ionic, 1.9 and above. What's the difference between chlorine and hydrogen in terms of electronegativity? 1.4. It falls under the polar covalent bond, so it will. Okay? Does that make sense to you all? Now, if there's a container of gasoline that is on fire, should you extinguish it with water? Why? You shouldn't. Because gasoline is lighter than water, not going to mix with water, and it's going to just splash all around. When I was in high school, we had like a bunch of chemistry nerds, and our lab instructor, it was very different back then. It was 40 years ago. No, 30 years ago. More than 30 years ago. Our lab instructor took a beaker, put some benzene into it, pretty close to gas, okay? Just a beaker, benzene, set it on fire, and told one of the girls, kill it. She did the first thing. She got another beaker full of water and poured it into the flaming one. All flaming gas ended up on the floor, and now we have a giant fire on the floor. She eventually took it out using sand, but she had a fire blanket. She just forgot about it. She was panicking. But everything could have been done much simpler. If there is a fire, just put the lid on it. Just kill the oxygen. That's it. Does that make sense? So if you have something like that, if you have burning oil in the kitchen, no water. It's going to make things way worse. Okay? Put the lid, have a small fire extinguisher, like stores have them like a little can. It will help. Okay? So we figured out that ionic compounds, they dissociate in water solutions. So overall, different compounds can be categorized as electrolytes or non-electrolytes. Electrolytes can be divided in turn into the strong electrolytes and weak electrolytes. So strong electrolytes, such as sodium hydroxide, sodium chloride, I'm tripping, such as sodium chloride, strong electrolytes will dissociate in water completely, and they will produce positive and negative ions. Do ions have a charge? That's a stupid question, I know. Do they? Yes. When charges move in certain direction, like negative charges move or positive charges move, can we classify it as a current? Yeah? When charges move, can we say that it's a current?
Yes.
And since particles are charged, that's electrical current. So the idea is that strong electrolytes form solutions that can conduct electricity very efficiently. Okay? Does that make sense to you? Okay? So, and the greater concentration of a salt will give greater concentration of charged particles, which means they're going to be much better, conductors of electricity. Weak electrolytes poorly conduct electricity because weak electrolytes do not completely dissociate in water. If you would look at the scheme on the right, you will see that hydrofluoric acid, hydrogen fluoride, when dissolved in water, a huge chunk of it remains as the molecule where hydrogen and fluorine form a covalent bond. Well, it's partially ionic. And some of it is actually dissociated. So the concentration of ions is much smaller, which means they not really conduct electricity well. And then we have non-electrolytes. So I don't know why these folks are so hung up on methanol. I would use sugar, simple sugar. Sugar does not dissociate, okay? So when you dissolve sugar in water, it exists as individual sugar molecules. When you dissolve methanol in water, methanol exists as individual methanol molecules. So no ions, no conduction of electricity. Okay? Sounds good? Now, how can it become practical? Well, if there is a body of water, like Lake Erie or an ocean, do they have salts dissolved? Some salts. Yeah. Even lake water, there's some salt. We call it, fresh water, but there are some salts. What's going to happen if you will take an electrical cable and throw it, cut it, like hot cable, throw it in the water? Water will conduct the electricity because, there are some salts, right? Am I making sense? Same is going to happen if you're going to pee on a live wire. And believe me, in Mother Russia, there were numerous cases when people got belligerently drunk and did not see where they peeing, and what was left of them. And there were cases when people did that with really, really a big transformator thing, and they got killed. Okay?
Wow, that's horrible.
Yeah. So this is just a classification of electrolytes. Basically, all soluble salts and strong acids and bases. We didn't talk about them. We're going to get back to those. Weak acids, like acetic acid, for example, or weak bases, such as ammonia, aren't great electrolytes. And various polar organic compounds are non-electrolytes at all. So, calcium chloride, right? How does it, do you think, how does it dissociate in water? It's a strong electrolyte. So since it's a strong electrolyte, does it dissociate? Yes. Does it dissociate completely? Yes. So, not A. The question is B or C?
C.
Exactly. You understand why? Because we have two chloride anions. And this shows you that there are two chloride anions that are independent. In other words, if this is calcium ion, and these are two chlorides, right? When they dissociate, you have a separate calcium and two separate chlorides. Right? Okay, makes sense. Now, potassium phosphate, strong electrolyte, salt. Which equation is correct? Remember, this is the polyatomic anion. So how does it behave? Remember, it behaves as an individual unit. Does it make sense? So, this is the schematic representation of the salt. Okay? So when they separate, when they dissociate, you have 3 potassium ions and 1 phosphate. Does that make sense?
So it'll be A.
Yes. Selecting C is incorrect. I saw it. Students do it. So just, don't. So, question, which of these 4 reactions represents the dissociation of a strong electrolyte? The dissociation. Yeah, it is C. So sodium sulfate. Dissociation means you start with like everything together and end with things that are dissociated. Clear? Okay. So, we're going to write some equations here. So, dissociation of potassium chromate should be capital O. Okay? So, it's a strong electrolyte. Does it dissociate completely? It's a strong electrolyte. Strong electrolyte always dissociates completely. This CrO4, this is polyatomic anion. So, first of all, complete dissociation means a single arrow from left to right. Okay? And we're going to add this symbol S, solid. So when potassium chromate dissociates, what are the ions that are formed?
So 2K?
2Ks. What is the charge on potassium?
Positive.
How many? Which group is it in?
Group 1.
Which group? Yes, 1, yes. So 2 positive charges and chromate, right? just one. How many charges on chromate? Say again?
I wouldn't say 4.
Why?
I was going off the 4 at the subscript at the bottom, but
Why? Subscript at the bottom just shows you that it's 4 oxygens.
okay.
How many charges do we have on the left? Do you see any charges on the left?
No.
So 0.
Yeah.
How many charges do we have on the right now?
0.
No. We have 2 positive charges, right? We have to have 0, right? So it's got to be to offset 2 positive charges. How many negatives do we need?
2.
Also 2.
Oh.
Okay? And we put AQ
Ugh. Probably was done with that.
next to each ion. Okay? Now, phosphoric acid is a weak electrolyte. How many arrows? 2, right? That shows from left to right, and also that it goes back. And it will dissociate. I'm not going to torture you. 1 hydrogen is going to fall off. And what we have left is dihydrogen phosphate, an ion. Okay? Both of them are in the aqueous solution. Okay? This is not a fair example because the first sort of temptation is to say, oh, 3 hydrogens and a phosphate, but it never gets to that point. It's super weak. Each next hydrogen is even harder to pull off. Solid sugar. Will sugar dissociate? It is not salt, okay, so it cannot produce ions. Will it dissociate?
Yes.
No.
No.
You have to have,
No.
you have to, when it dissolves, we still put 1 arrow, but it's going to be this. It's going to be the whole molecule, just in the aqueous solution. Okay? That makes sense? I think what we're going to talk about now, we're going to talk about, well, we'll see like equivalence maybe a little bit more, and I'm going to let you out slightly earlier. So, equivalent. Equivalent is the amount of an ion which carries 1 mole of positive or negative electrical charges. Okay? Usually, for expressing the concentrations of ions in the blood, instead of equivalents, we use milli equivalents. Obviously, 1,000 milli equivalents is 1 equivalent. So, here's the deal. If you have a mix of sodium chloride and potassium chloride, and you know that in this mix there are 25 milli equivalents of sodium and 4 milli equivalents of potassium, what's the total number of charges? 29. 25 plus 4, right? Does that make sense? That's the total concentration of positive charges is 29 milli equivalents per liter. So the total amount of negative charges must be the same, because it has to be electrically neutral. So I want to stop here and discuss some things with you. Okay? So, what is a mole? What is a mole? More specific, what kind of measurement? Because remember, it's not a measure. It's a unit, yes. But like a meter is a measurement, it's a measured unit. Is mole a measured unit? If it's not, then what type of unit is it? Counted, right? It's a counted unit. Make sense? It's a number. Okay? So, let's say we have 1 mole. Remember, mole is a number. We have 1 mole of sodium ions. So how many charges that mole is going to carry?
1.
1 mole. No. That entire mole is going to carry 1 mole of positive charges. Is that clear?
Yes.
1 ion has 1 dozen ions of a dozen charges. 1 mole of ions has 1 mole of charges. Okay? Now, we have 1 mole of calcium. How many charges? How many moles of charges? 2, right, because each calcium carries 2 charges. Now, the definition of an equivalent. 1 equivalent is 1 mole of charges, number-wise. Is it clear? 2 moles of charges will be 2 equivalents. Is it clear? So this is why, yes.
What if it's three charges?
3 equivalents.
3 moles.
1 mole will give you 3 moles of charges, which means 3 equivalents. Does that make sense?
Okay, if it's 3 charges, then that will give us 3 moles of 3 positive charges.
Okay, so let's talk about the iron, right? So we have 1 mole of iron, 3 cations. Remember, a mole is a number. How many moles of positive charges it will give us?
3.
Yes.
So as the charge increases, the number of moles increases, right?
Moles of charges increases, and it means that it's going to be 3 equivalents. Okay? So I am not aware of any ions with a charge 4, but if there would be any, 1 ion would give us 4. 1 mole of such ions would be the same as 4 equivalents. Okay? Go ahead.
Well, I thought it would have, like, you're trying to describe it as, like, we have a bunch of hydrogens or heliums, and it's in this mole. So it'd be like, if there's 5 heliums.
Helium is not charged.
If there's 5 hydrogens, then it would be 1 mole of 5 hydrogen charges. 5 positive charges.
5 hydrogens means 5 atoms of hydrogen? Yeah? Well, mole is the number. So if there are 5 hydrogens, there's no mole anywhere near, because the mole is 6.02 by 10 in the power of 23. So, if you ask me frankly, I always thought that equivalents were invented by doctors to, sound smarter than they really are, because you really don't need equivalents. moles are fine, but for some reason, I know the reason, because we have, let's say if you have only one negatively charged ion, but a bunch of positively charged ions, and your solution is electrically neutral, then all equivalents of your positively charged ions added together will give you the equivalent of a negative charged ion, because the average should be the same. So this is an example of calculations, okay? What I want to do the calculations on our own, okay? Because it's better than me reading this all. So this is the first question. Blood calcium is 8.8 milliequivalents per liter. So let's do some calculations, shall we? So what we know is 8.8 milliequivalents per liter. We somehow need to get to the moles of calcium, right? In half a liter. So first we need to get from milliequivalents per liter to just milliequivalents. So what is the volume? Volume is 0.5, okay? So what I do, I say 0.5 liters contain that amount of milliequivalents. I use the concentration of calcium as a conversion factor. Are you with me? Do we cancel liters out? Is that all good? Agreed? Now, we do have the establishment that, so here's my question. 1 mole of double charged calcium, how many equivalents does it provide? Is that a conversion factor? Yes. Now, these are equivalents, these are milliequivalents. So another conversion factor that we need to write down. 1 equivalent contains how many milliequivalents?
1.
It can be that different. 1 equivalent contains how many milliequivalents? Huh? 1,000, yes. So these are the conversion factors that we will need. Okay? So first we need to convert 4.4 milliequivalents into equivalents. So we use that second conversion factor, okay, which gives us, I'm going to use scientific notation, 4.4 10 to the power of -3 equivalents. Okay? Trust me. It's going to be this. Now we need to go from equivalents to moles. Correct? So we are going to use this conversion factor. Since I am going from, sorry, my bad, didn't put the units. Since I'm going from equivalents to moles, equivalents have to be on the bottom, moles have to be on top, and for calcium, it's going to look like this. So it gives us 2.2 10 in the negative 3 moles. This is essentially the same. Make sense, everybody? Okay. Now, this is if the only other anion, negatively charged ion, that is present is chloride, how many equivalents? It's got to be the same. If calcium is at 8.8 milliequivalents per liter, well, chloride has to be the same. Okay? So, yeah, you have electrolytes in the plasma. These are, okay. So I don't know why this is all here. There are electrolytes in our solutions. Let's just skip it. So, quick learning check, and I think where we at? Yeah, it's gonna take some time. Yeah, we're gonna stop at this. We did amazing. So here, 1 mole of iron 3. How many equivalents? 3. 2.5 moles of sulfate. How many equivalents? Say again? 5. It doesn't matter. Sign doesn't matter. It's only charges. And if sodium is 34 milliequivalents per liter, chloride should be 34. Remember, this is what? This is the charges. This is not the concentration. Okay? So for instance, if you have the salt, such as calcium chloride, here's my question. Listen, it's actually a pretty good conversation right now. So we have 1 mole of calcium chloride. Okay? So calcium chloride will dissociate into calcium and chloride. Okay? So how many, how many chloride ions it will generate? 2. So if 1 mole of calcium chloride will dissociate, how many moles of calcium ions we're going to get? There's 1 mole of this. How many moles of calcium ions?
1.
1 mole, yeah. How many moles of chloride ions? 2, yeah. Does that make sense? So the concentrations, actually, the amounts of ions can be different. But when we start talking about equivalents, we basically get down to charges. Because that's what we care about when we talk about solutions. They have to be electrically neutral. Sounds good? All right. So we're going to continue the conversation about solutions. We talked about this stuff last week. So now the idea is to talk about solubility. Now, give me a second. I'm going to change the lights. It's chapter 9. All right, folks. So, the example that they use here is the gout or gouty arthritis due to the accumulation of uric acid in the joints. This condition often affects men, middle-aged men. Luckily, I'm not one of them. Okay, so we're going to talk about saturation of solutions and the rules of solubility. So the definition of a solubility is the maximum amount of solute that can be dissolved in a certain amount of solvent. So usually we express solubility in the grams of solute per 100 grams of water. Well, or whatever solvent we are talking about, but to be honest, we're going to be focusing on water for the most part. Okay? So important to understand that the temperature affects solubility quite dramatically. So, and in terms of solubility, I want you to understand the concept of saturated versus unsaturated solutions. Unsaturated solutions, they can still dissolve a solid. For instance, you can add certain amount of salt to water, it will dissolve, then you add more salt, it dissolves again, and as long as it can be dissolved, the solution remains unsaturated. Okay? So in unsaturated solutions, you do not reach solubility. When does solution become saturated? When you cannot dissolve any more solute in it. In other words, saturated solution contains the maximum amount of solute and reaches solubility. You can try this at home and just start adding, say, baking soda or table salt to a certain amount of water and see when it stops dissolving anymore. So essentially in a saturated solution like this, there is an equilibrium between the solutes that are dissolved and the solutes that stay in a solid phase. When you think about physical processes like that, or chemical processes, name it whatever, I want you to understand that it's not a static system. Some particles, let's use the term molecules if we talk about a sugar solution. Some molecules of sugar will recrystallize into the solid phase, while some molecules of sugar from the solid phase will dissolve and transfer into the liquid phase. So that's sort of unfortunate that people who created the slides didn't know all the tricks of the trade, but what should be here are two arrows. The top arrow that runs from left to right shows you the process of dissolution, and the bottom arrow from right to left shows you the process of recrystallization. So, when you add salt to the water, and it keeps on disappearing, is it saturated or still unsaturated? Saturated. No, still disappears. You can add more. It's not saturated yet, so still disappears. Does that make sense? Yes? So, but when you add a solute to water and that solute does not disappear and remains on the bottom, it means that this solution cannot, quote unquote, accept any more solute. Okay? So it is saturated. Now, this is a very interesting exercise in a good way. So it shows you the solubility of potassium bromide at a certain temperature, which is in this case the solubility, 80 grams per 100 grams of water. Okay? And the question that we pose here is to distinguish or characterize the solutions A, B, and C as saturated or unsaturated. So if you dissolve 60 grams of potassium bromide in 100 grams of water, is it more or less than the solubility of potassium bromide? Less. And what does that mean from the standpoint of solution saturation? Unsaturated. Now, 200 grams of potassium bromide in 200 grams of water, saturated or unsaturated? Saturated. Because, hear me out, if the solubility is 60 grams per 100 grams, it can be expressed as 120 over 200, right? And in this case, we add not 120, but 200, sorry. Solubility is 80. Okay. So, 200 gram of potassium bromide in 200 grams of water is more than the solubility. And finally, 25 grams potassium bromide in 50 grams of water. What do you think? Unsaturated. Unsaturated. Okay. Questions? All good? So we're going to get through this. Now, with the increase in temperature, solubility increases, for the most part. Okay? That make sense? Overall, the hotter the solution, the more solute you can dissolve in it, unless this solute is a gas. When temperature increases, the solubility of gases decreases. Does that make sense? Does anyone fish? No? 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 If it's really, really hot outside, where would fish be? On top of the lake or in the bottom of the lake? Why? And no. With the increased temperature, what happens to the solubility of gases? Decreases. Which means in the hot water, the warm water, there will be more or less oxygen.
Yes.
Less oxygen. They go to the cooler layers, which have more oxygen. Does that make sense? I find this graph just sort of interesting. I'm going to mention only two relevant, really, household items. One is sodium chloride. You see that its solubility doesn't really change much with temperature. Okay? Which means if you add salt to the cold water or to the boiling water, the same. Okay? And another one, of course, is glucose, which is really interesting. So at the room temperature, its solubility is, let's say, 80 grams, right? Per 100 grams of water, which is still kind of insane. Okay? At the temperature of about 52, 53 degrees Celsius, which is not that hot, its solubility reaches 200 grams per 100 grams of water. And it keeps growing. Okay? Makes sense? So if you boil water, you can dissolve an insane amount of sugar in boiling water. Okay. So, a good question. When you take a bottle of Coca-Cola and leave it in the heat, why can it explode?
Because of the gases expand.
Because the solubility of gases as temperature rises. Gases.
Expand.
Not only that, the solubility of gases in water. When the temperature goes up, the solubility increases or decreases? Decreases, right? So carbon dioxide leaves Coca-Cola, gets accumulated under the cap, and yes, you're right, gas expands, and more gas comes out from the solution, and it expands, okay? I think we already answered that question. Like, seriously, if it gets too hot, it can die. And now we jump to what's called Henry's law. This is quite an important law, and I will explain why. So, it states that the solubility of gas in a liquid is proportional to the pressure of that gas above the liquid. Okay? So the greater the pressure, the more gas molecules can dissolve in the liquid. Okay? So if you look at this illustration right here, you can see that when you open a can of Diet Coke, for example, carbon dioxide that was accumulated leaves, and the overall concentration of CO2 above the surface of Diet Coke drops, right? Which means all those CO2 molecules start evacuating from your Diet Coke, and after a short period of time, it becomes flat. Okay? Right? Makes sense? Why is that important? That's a quick digression into physiology, because all of you go into some kind of a medical professional field, I presume, right? So, the pressure of oxygen at the sea level is approximately 152 torr. Okay? And that concentration, that pressure of oxygen, determines the concentration of oxygen in the human blood. Hemoglobin saturation. Does that make sense? So the hemoglobin saturation would be, I don't know, let's give it 97% saturation. If we go really, really up in the mountains, let's say like considerably high in the mountains, where the pressure of oxygen is 100 torr, when the pressure of oxygen drops, according to Henry's law, what's going to happen to the concentration of oxygen in the blood? It will also drop, right? So now you have saturation not 97, but let's say 87%. It's not a direct relationship, so. But the point is that if you ever travel to a place with the mountains, and you were in the mountains, about 2.5 miles, you start noticing that. And if you go 4 or 5, well, like 3 miles, 4 miles, then it becomes like 4 miles, 5 miles. You cannot survive without an oxygen tank, pretty much. Unless you have a very, very special training. Okay? So, how do we know which ionic compounds are soluble or not. So what you see here is called a solubility rule. Okay? How do you use them? These are, for our intents and purposes, universal rules. What do they mean? They mean that an ionic compound that contains either the 6 positive ions, no matter what an ion is, will be soluble. Does that make sense? Now, if you take a look at periodic table, you will see that first 5 ions, lithium, sodium, potassium, rubidium, and cesium, all belong to the first group in periodic table. Okay, does that make sense? So you can think of it this way. First group, soluble, plus ammonia. Doesn't matter what salt is. You know, sodium silicate, phosphate, acetate, you name it. Then we have, what about negative ions? Any salt that contains nitrate is soluble. Salt that contains acetate is soluble, no matter what cation is. Does it make sense to you all? Yes? Chlorine, bromine, and iodine, they form anions. These anions are only insoluble if combined with silver, lead, or that specific type of mercury. Okay? Sulfates, soluble unless the cation is barium, lead, calcium, strontium, or mercury. Okay? So, this is just like, this is some, in my opinion, mildly relevant idea here, that barium sulfate is used to enhance X-ray of the gut, because gut is the soft tissue. Okay? But we can practice quite a few solubility rules. What I want from you is to tell me why a certain compound is soluble, right? So potassium sulfide. Why is it soluble? Potassium. Calcium nitrate. Soluble because nitrate. Now, look. Lead 2 chloride. Okay? I know that you can read the information on the table. It's fine, I understand. But the logic behind it. So you think about, okay, what about the cation? Cation is a lead. So it looks suspicious. What about the anion? Generally, chlorides are soluble except these. Therefore, insoluble. Okay? Sodium hydroxide. Soluble because of sodium. Aluminum phosphate. Aluminum is not in the list of cations. And phosphate is not in the list of anions. So, insoluble. So, let's answer some questions here. And cadmium sulfate, okay? Right, cadmium sulfide. Insoluble because neither cadmium nor sulfide are in the list of the solubility rules. Iron sulfide, same idea. lead to iodide. Generally, iodides are soluble unless it is silver, lead, or mercury. Nickel hydroxide. Neither of the ions is in the solubility rules. Does that make sense? Yes, no, maybe? Some practice? Barium nitrate. You have the notes. I'm not going to scroll back. Soluble or insoluble? Go back. Read your notes. Yeah. Soluble or insoluble? Is barium in the list of first group plus ammonia? Dude. No. Barium is in the second group, right? So barium immediately causes suspicions, but then we'll look at the nitrate and ion. What do the rules say? Huh? No. Nitrate is not positive. It's negative because it's an ion, but soluble? Soluble? Soluble, right? Does that make sense? Soluble?
Yes.
Yes, potassium, first group. Okay? Potassium, folks, instead of memorizing 6 separate cations, look at the periodic table again. Do you see the first group? Lithium, sodium, potassium, rubidium, cesium. These are your 5 out of 6. You don't even need to memorize them. Just remember group 1 plus ammonia. That's it. Okay? Calcium sulfate. Now, sulfates. Many of them are soluble unless it's calcium. Okay? That makes sense? Right. Okay, let's go back to this. Yeah. So now we're going to talk about the concentration, and I want you to acknowledge that the concentration is something that you maybe unconsciously use when you go grocery shopping. Okay? So hear me out. When you buy vegetables or, I don't know, apples, potatoes, sometimes do you buy bags, right? Like a bag of potatoes or a bag of oranges. When you buy a 5-pound bag of potatoes, you can say that the concentration of potatoes is 5 pounds per bag. Does that make sense? So if I tell you, go and buy 25 pounds of potatoes, how many 5-pound bags are you going to get?
5.
Treat concentrations like potatoes in the bag. It makes life so much easier, okay? So we're going to learn about different ways to express the concentration of a solution. First of all, the definition. Concentration is a fraction, which is written as the amount of solute divided by the amount of the solution. It can be expressed as mass percent, mass of solute per mass of solution, volume percent, volume of solute over the volume of the solution, mass volume percent, mass of solute over the volume of the solution, and molarity, which is moles of solute per liter of the solution. I want to specify something very important. This word, the solution, implies that it's the volume not of a solvent. Does that make sense? When you dissolve 40 milliliters of ethanol in 60 milliliters of water, and consider that the volume is an additive property, what's going to be the total volume of the solution? 100, right? So it's always the volume or the mass of the solution. So what is the mass percent? Mass percent is the easiest concentration to calculate, to be honest, and to prepare. So grams of solute divided by the grams of solute plus grams of solvent multiplied by 100. That's your mass percent concentration. Okay? Sounds good? So here's an example. Mass of water is 8 grams. Agreed? Sorry, not water, potassium iodide. Mass of water is mass of solution, actually, is 50 grams. The concentration, 8 divided by 50, multiplied by 100, so 16%. Now, before we move on, I have an important question for you. Seriously. Do you understand what an additive property is? It's worth explaining. It's not for the exam, but it's something that is worth to know. So, let's say my body mass is 200 pounds. Okay? I put on the vest, which weighs, say, 10 pounds. The mass of me with the vest, what's going to be? 210, right? This is called an additive property. I'm going to give you another example. We use that example, 60 milliliters of water and add to it 40 milliliters of ethanol, forming a solution. What will be the final volume of the solution? The right answer is we don't know, because volume is not an additive property. When you mix a solute and the solution, the volume of the solute and the solvent, the volume of the solution may not reflect the added volumes of two. Okay? Here's an example. Imagine that you have 100 milliliters of water and you have 5 grams of sodium chloride, which occupy like a teaspoon. When you will dissolve sodium chloride, the volume of the solution will still be about 100 mils. If it's going to change, it's going to change minimally. not by 5 milliliters. This is why we have to be very careful. Volume is not an additive property. Mass is. Now, okay, calculating volume percent, I think it's not a rocket science right here. So if I ask you to prepare that solution, you can literally take 42 grams of water, add 8 grams of potassium chloride, and be sure that that's going to be the correct solution, 16%. Am I clear? If you know the mass of solvent and you know the mass of solution, you know the mass, the concentration, the mass percent concentration. So here's the thing. Let's talk about this. So you have 15 grams of sodium carbonate and 235 grams of water. Here's the first question. What is a solute? What is a solvent here?
Water is solvent.
And sodium carbonate, solute. So mass percent concentration can be expressed as the mass of solute, I'm not writing mass, divided by the sum of the solute and solvent masses, which is 15 gram divided by 15 gram plus 235 gram. Okay? Which is 15 over 250, which is 6%. Okay? Skipping the... Okay, volume percent. Pay attention. This is the definition, but we will not have the calculations in which we will add the volume of the solute and the volume of the solution, solvent together. Okay? So, milliliters of solute that you added and over 100 milliliters of the solution. Okay? So, here's an example, which, due to my ethnic origins, I take great pride in talking about. When you buy vodka, no, seriously, when you look at the concentration, right, it says 40% ABV. Does anyone know what ABV stands for? Alcohol by volume. Okay, in other words, it's 40% volume by volume solution. Okay? But a little bit to kind of maybe lighten up the conversation. A lot of countries claim that they were the first to invent vodka. Russia is one of them. Moreover, Russians attribute the development of the modern recipe for Russian vodka to Dmitry Mendeleev, the same guy who developed the periodic table. Historically, it is kind of true. Mendeleev set the government standard for vodka. There is one little insignificant detail. He was the head of the standards, like state agency for setting up standards. He set the standard not as the volume percent, but as a mass percent. So it was 40 grams of ethanol in 100 grams of the solution. You can calculate it but basically the volume percent in this case would be much higher. So the quote-unquote original Russian vodka was stronger, but eventually, I don't know what happened. They're all doing volume by volume. I don't really see a problem with it. Okay. Mass volume percent. Mass of a solute in 100 mils of the solution. This is the standard. I want you to pay attention. Not a liter, not 10 milliliters. 100 ml. Okay? So, let's summarize this calculations. So for this, the conversion factor would be, what does that mean? 8.50%. It means 8.50 gram of sodium hydroxide in 100 gram of solution. Okay? Sounds reasonable. We just did that, so 5.75 milliliters of ethanol per 100 milliliters of the solution. And in this case, okay, 4.8 grams of hydrogen chloride in 100 milliliters of the solution. Okay? All good? Any questions? Okay, let's move on. Before we get to dilutions, for some reason, there is no conversation about molarity. Remember we were doing the lab this Monday? Okay? And you had solutions that were called, you were preparing the buffer, remember? And it was 0.1 molar sodium carbonate. So this term, the big letter M, it means that there is 0.1 mole of sodium carbonate in 1 liter of this solution. Does that make sense to you? Awesome. So, dilution. We increase the volume of the solvent, right? Specifically, only adding solvent, thereby reducing the concentration. So, when we talk about the aqueous solutions, we add water, volume goes up, the concentration goes down, and this is very important. When you add water, the amount of solute does not change, okay? So this is the universal equation to go from one concentration in volume to another concentration in volume. Now, hear me out. Let's say we're talking about solution with certain molarity, right? So let's say we have 0.1 molar solution of sodium chloride, okay? What it means is that there is 0.1 moles of sodium chloride in 1 liter of the solution. That makes sense? All good? What if we have 0.5 liters of that solution? How many moles of sodium chloride we're going to have in that volume, in the 0.5 liters? We're going to have 0.05 moles. Does that make sense, what I'm doing? No? Not really? Okay. I'm kind of setting the stage, okay? So let's talk about something that is more tangible, or at least you can see it on the shelf. Again, vodka, okay? For the reason it's easy to express the concentration, right? So vodka contains 40%, and it's a volume percent, of ethanol. Does that make sense? So it means that for every 100 milliliters of vodka, in those 100 milliliters, you're going to find 40 milliliters of ethanol. Does that statement make sense? Okay, good? Cool. So I purchase a 750 milliliter bottle of vodka. The question is, how much ethanol is in that bottle? Clear? Okay? So these units cancel each other out. And what do we have? We have 300 milliliters of ethanol. Okay? Listen, this is not the end of the story. I'm taking this bottle of vodka, okay? Hear me out. That's 750. And I mix it with water, so the final volume is 1.5 liter. Let's say I mix it with 750 milliliters of water. Are you with me? So, new volume is 1.5 liters. Okay? What is the concentration then? You have 300 ml, you with me, of ethanol, but the new volume is 1500 milliliters of, well, it's not vodka anymore, but you get the drift. So calculating, it's going to be 20%. Okay? Why I did all this math in front of you? Because I wanted to emphasize that when you make dilutions, the amount of solute does not change. Okay? So this is why we can write this equivalency here, that the concentration of the initial solution multiplied by the volume of the initial solution, basically the amount of solute, remains the same. Okay? So here's an example. We have concentration 1, volume 1. We have concentration 2 and volume 2. Let's identify the concentration 1. Okay? Concentration 1 is 9%. volume 1 is 10%. Volume 2 is, sorry, not 10%, 10 ml, my bad. Volume 2 is 60 ml. So we write this, 9% multiplied by 10 milliliter equals C2 multiplied by 60 milliliters. Okay? Can we find C2 out of this equation? The concentration changes. So, look, volume goes up from 10 to 60. The concentration goes down from 9 to 1.5. Okay, we can skip this. Okay, so let's identify. This is your volume 1. This is your concentration 1. This is your volume 2. Okay? If you don't mind, I'm not going to write all the C1, B1 equals C2, B2, okay? So, C2 equals C1 multiplied by V1 divided by V2, which means 0.600 multiplied by 0.180 over 0.540. Okay? That makes sense? Okay? This is just arithmetic. All right. Properties, it's pretty much sort of the last thing. We're going to talk about the true solutions, the colloids, and the suspensions. So what is the true solution? They have these three features. They are transparent, they do not separate, and they importantly contain small molecules or ions that you can't filter and you can't retain using semi-permeable membrane. Okay? The colloids have medium-sized particles. Also cannot be filtered, but can be separated by semi-permeable membrane. Okay? So these are colloids. Colloids can technically settle, but it takes a very, very, very long time. Okay? So liquid in the gas, clouds. Solid in the gas, such as smoke. Gas in liquid, whipped cream. Okay? Gas in solid, which is a very weird characterization here. Liquid in liquid, yes. Homogenized milk. I don't remember if we had this conversation. Did we talk about milk? Yeah. Remember in the very beginning? This is why milk is homogenized. This is the reason. Because if you don't homogenize it, it's going to separate. So homogenization allows you to evenly distribute all the components of milk in a bottle. Cheese and butter, yes, liquid and solid. This is real important thing, blood plasma, because this is what enables the process known as dialysis. Since the blood is a colloid, it can be separated using semipermeable membrane. In other words, toxins, small molecules, wastes, can be moved out of the blood through the membrane, while the proteins of the blood are going to stay in the blood. Suspensions, heterogeneous mixtures, okay? Particles can settle out of the solution, can be filtered, and must be stirred to stay suspended. Now, you can clearly see that people who wrote examples are not biologists or physiologists, because blood platelets is a terrible example. They would just write blood. Blood is a suspension, okay? If you will stabilize it somehow so it doesn't clot and leave it, it will separate eventually. It's gonna take a while. The larger the particles in the suspension, the quicker it's going to separate. Okay? So this is the summary. I want you to think about it like this way. You can filter and you can use semipermeable membrane. If it's a solution, neither filter nor semipermeable membrane will affect its composition. If it's a colloid, filtration doesn't affect its composition, but the membrane does. It can retain some components of a colloid. If it's a suspension, we're not even getting to the membrane because the filtration will separate the suspended particles. Okay? So this is actually a really good illustration here. So solution is represented by the orange particles, you see. And the suspension is represented by the red, and colloid is by green. When you have this, let's say it's a blood, okay? And the red is blood cells. You can filter blood so that blood cells will remain on the filter while plasma goes through. Another way to do it is to spin the blood in the centrifuge. Cells will go down and the plasma will stay on top. Make sense? Now you take that plasma and you put it in the bag made out of semipermeable membrane. You can see that the protein components of plasma, such as albumin, the green parts, will stay within the bag, but the components like urea or sodium or chloride and whatever, they will freely move in and out of the bag because they form a true solution. Am I making sense? So, solid particles do not settle, but too large to pass through a membrane. Solution, colloid, or suspension? Excellent. Which brings us to the conversation about osmosis. So osmosis is the flow of water from the lower to the higher concentration of the solute. Think about it as water wants to dilute something, to dissolve something, right? Does that make sense? It always wants to go where it can reduce the concentration. Okay? And the important part is that this movement happens through semipermeable membrane, which means the water can move, but the solute cannot. Does it make sense to you? So solute is retained on one side of the membrane. And if you look at, let's say, a glass, a beaker, separated by the semipermeable membrane, and on the left just water, and on the right there's some kind of a solution, the water will move from left to right. Agreed? Which means, at some point, the level of solution on the right will go up, and the level of water on the left will go down because of that water flow. Does that make sense? Yeah? The liquid, if you put it in a tube, the column of liquid, does it exert a pressure? Yeah, it does. So the osmotic pressure is equivalent to the pressure of the fluid that would prevent osmosis. Okay? And the osmotic pressure depends directly on the number of the dissolved particles. Now, I will try to illustrate this. I want to highlight one important detail about this. In this conversation, do we ever talk about a nature of a solute? Is it a sucrose, a glucose? We don't. Osmosis depends on particles rather than a nature of them. Do you understand? Like if you have 5 molecules of sucrose or 5 molecules of lactose, they're going to draw water towards them equally well, because it's all about the number, not the nature. So, let's do that example one more time. So we have semipermeable membrane. We have the solution on the right, water on the left. In which direction will water flow? Left to right, because it goes towards greater solutes, right? And it will result in the increase in the level of the solution on the right. Agreed? Now, why the flow stops? Because the drive from left to right is canceled out by the extra pressure from that extra water. Does that make sense? Okay? So they will be in a balance like that. Okay? So that means that we can run osmosis backwards if we apply a pressure that's greater than osmotic. Okay? Am I making sense? So hear me out. Let's go back to our left beaker, shall we? The arrow that I'm about to draw represents osmotic pressure. Okay? If I will install a plunger right here, that will exert the same pressure on that specific compartment. The pressure that I exert will compensate for the osmotic pressure. There will be no movement. If the pressure that I apply is greater, we can force the water out. We can force the water back. Okay, make sense? So flow of water is reversed. Okay? So the water starts flowing from the area with high solute concentrations to the area with the low solute concentrations. Now, let's go back to that beaker one more time. If this is the situation that we're facing, this is the reverse osmosis, what's going to happen to the volume of that right compartment as you push the water out of it? Volume is going to decrease, right? But solutes, remember, they can't leave. So the concentration of solutes is going to be increasing because volume goes down. But what it means is that in this compartment, in the left one, the amount of water will go up. So this reverse osmosis is used, and it actually is used by some countries to produce pure, fresh water. Can you hypothesize which countries use reverse osmosis to produce high quality fresh water? Think about conditions. They should have very, very limited supply, and they should have insane energy resources.
Like Arab countries?
Rich Arab countries on the Arab Peninsula. To my knowledge, all fresh water in Kuwait is produced by reverse osmosis. They can afford that. That's ridiculously expensive, but since the oil is cheap for them, they can afford that. The last thing to talk about is tonicity and dialysis. So isotonic solution, okay, has the same osmotic pressure as bodily fluids, which means there is no net flow of water in or out. Make sense? So imagine you have a cell with a concentration 0.9% in the solution with a concentration of 0.9%. Those concentrations are equal, right? So water does not flow in or out. So cell remains intact. Typical isotonic solutions that are used in medicine, 5% mass volume glucose or 90% mass volume sodium chloride. 0.9%, I'm sorry. Hypertonic solution has the lower solid concentration. So check this out. Imagine that you have a cell with a concentration of 0.9%, and you put it in distilled water, which effectively has no solutes. In osmosis, in which direction does water flow? No. Concentrations of the solutions in osmosis. In terms of solute concentrations, water moves to where? Inside, in this case, to the higher concentration of solutes, right? So that's your hypotonic because it's less concentrated than the cell, and the water moves from hypotonic solution into the cell, and they swell and burst eventually. Okay, makes sense? Yes? And if you will inject distilled water into somebody's veins, this is what's going to happen. You're going to create hypertonic environment. Their red blood cells will hemolyze, and it's going to kill their kidneys. Hypertonic solution is the opposite. Let's say we have 0.9% cell and 2% salt on the outside. Water will be leaving the cell, resulting in the crenation. So cells will shrivel. Sounds good? Now, the dialysis is when the solvent and small particles pass through the membrane. You can see it in this illustration. You put a dialysis bag with a solution in it, and small solutes, such as sodium chloride, for example, will get out of the bag, while large particles, such as protein particles, will remain there. Okay? Make sense? Why we care? Because during hemodialysis or artificial kidneys, when somebody's blood is run through these kidneys, the membrane allows the removal of small waste particles such as urea while keeping important proteins like albumin in the blood. So I'm going to remind you 0.9% sodium chloride or 5% glucose. Those are isotonic solutions. So 1. Isotonic, hypotonic, hypertonic. 2% of sodium chloride compared to 0.9. Can you say which number is bigger? Which number is bigger, 2 or 0.9? Which means it's hypertonic. 1% glucose compared to 5. Which is smaller?
5.
Dude, smaller. 1%, which means 1% is hypotonic, okay? Because the concentration is lower than the isotonic concentration of glucose. Am I making sense? 0.5 sodium chloride. Hypotonic. And 5% glucose. Is it A? A. What's going to happen to cells, again, or 0.9%. What's going to happen to cells in this solution? Is it isotonic? So nothing. 1% glucose. It's what? 1% glucose solution is hypotonic. What happens to cells in hypotonic solution? The water moves where? To greater concentration, right? Which is in the cell. When water moves in the cell, what happens to the cell? It's going to burst. Okay, does that make sense? 0.5% sodium chloride. B, same story. 2% sodium chloride. Yes. Oh, wait, what's going on here? Oh, yeah, it's a solution. Okay.